let's pick up just briefly where we left off. We had this, or pretty much this. I think uh, y'all came up with roughly the same subtractor program or Turing machine, right? So, and one of the things that seemed to bother both you guys and the other class was the way that the borrowing worked, right? So when you guys did borrowing back in grade school, you kind of worked to the left and then you came back to the right. Okay, and that's fine, right? It's a perfectly good way of doing the arithmetic when you're teaching children. Um, I guess what we've sort of noticed is that, well, at least in binary, you don't have to do it that way. Could you do it that way with the Turing machine? Sure. Okay. What would need to change? Well, you might need to have extra symbols and or extra states. Okay. So for example, let's say that you're doing the subtraction and you reach a digit position where you need to do some borrowing. Well, you probably need to mark that somehow as, hey, this is the first place where I needed to do a subtraction that generated a borrow. So let me switch the symbol from a 0 or a 1 or whatever it is to like a, a T or an O or whatever, right? So you certainly are free to use extra symbols and extra states in order to do it. Um, but it turned out that it wasn't really necessary, at least in this binary case. Okay. So there might be more than one way to do it, and that's fine, right? Um, your Turing machines don't all have to look the same. And in some sense, it's almost better if they don't, because then it's more interesting, right? We've got different things we can look at. So on the subject then, for the Turing machine assignment, there's two of them. You guys probably saw there's a Turing machines A and Turing machines B. So Turing machine A, I've given you the Turing machine and the initial state of the tape, and your job is to go through the steps of execution. Okay. Turing machines B, there's two questions, and basically all you have to do is give me a URL to where you've done it in the simulator for the two things. So the first Turing machine problem is, well, how did we negate a number in binary? What was the procedure when you did two's complement? You flip all the bits and then add one. Okay. Um, Now, do we have a Turing machine that can do the add one part? Yeah, that was our first example. Okay, so we already have that part. Do we have a Turing machine that'll flip all the bits? Not yet. That's y'all's assignment, is to make the Turing machine that can do that. Okay, and then the second one is, well, this program we wrote, or this Turing machine we built, right, is a -1 machine, but in binary, right? So it decrements or takes one away from a given input value. Did we have to do it in binary? Could we have done this in base 10 instead? Yeah, okay. What's going to change if we do this in base 10? Huh? Either a lot more steps or, well, first off, there's a lot more symbols, right? Because how many digits do you have that you have to consider in base 10? Well, 10, the digits 0 through 9, okay? So there will be more lines of the table because you now have more different, so you probably have the same or very similar states. But for example, with subtract, how many cases are you going to have now that you have to consider? 11. Why 11? The x is so you've got 10, the digits 0 through 9, and then also the x. Okay, so it'll look similar to this in some sense. Okay, but it'll change because now you have more symbols to work with. Okay, and maybe you'll find that adding in an extra case or sorry, not case, a state is helpful. Maybe you can just do with these states. What did we have? Start, subtract, borrow, return, and halt. Right. So that's what, 5. Yeah, whatever. Um, so maybe that is sufficient, and we'll see. Okay. Now, the good thing is, of course, you're not doing that one in a vacuum. You have a model for what -1 looks like. It's just the binary example. And the question is, okay, how could you sort of scale that up to handle it in base 10? Okay. Now, one thing I want to be clear about, well, a couple things. Did we really have to put these X's in front on either side? No, we don't have to, right? That was just a convention that we used for sake of demonstration. It's a convenient enough one, so we'll just sort of stick with it. In this machine or the simulator, you can have it check for spaces. And so how do you type a space in the code? You use the underscore, okay, not an actual space. So you can certainly use space as one of your symbols, but you just type it as the underscore. And you can use pretty much anything else as a symbol, with a few exceptions, which it lists down below. So for example, you can't use star as a symbol. That's why we had to change to using X instead of star. And you can't use, I think, exclamation point as a symbol. That means something else. Yeah, so, but yeah, you mostly have carte blanche to do what you want. Okay, the last thing is to really make sure that we're clear. What kind of, does this program or this Turing machine really do subtraction? Yes and no. Okay, so yes, but what kind of subtraction does it do? It always does -1, right? So it gives a number and it takes one away from that. So that's not truly subtraction, is it? Right? Because to do true subtraction, how many numbers would I need? Well, I need two numbers, right? The thing to take away from the other thing or something, right? And what could those numbers be? Well, who knows, right? So yeah, this is not a general subtraction program, or in the same way that we didn't see a general addition program. But one of the things I like about this simulator is that it does have lots of examples. So let's look at this one. This is their binary addition program, right? And as you can see, it has 30 something lines in the table with a whole bunch of different states, okay? And let's run it, for example, and just kind of watch it run. It's kind of interesting. Okay, so it uses X and Y as sort of temporary symbols as it's going through. And essentially, what this is doing is, well, we'll talk about sort of the structure of how it's actually doing the addition in a second. But you notice it didn't do it all in one swell foop. It kind of went back and forth between the two numbers, okay, in kind of a what may seem like super inefficient, but is actually kind of clever, um, maybe in some sense. Okay. All right. Now, would you guys agree that this is starting to get like this Turing machine starts to demonstrate how impractical Turing machines are for actual computation, right? They're great as a theoretical construct, but they're not very practical in terms of actually doing stuff. Okay. So what we want to do is kind of abstract away from the Turing machine a little bit, but not too far, because we want to make sure that everything that we do when we abstract is still Turing machine doable, okay, or what I'll call Turing complete. Okay, so what does Turing complete mean? It can be done by a Turing machine, right? It might be a really, really gnarly, complicated Turing machine, but a Turing machine can do it, okay? And computable means that you can be done by a Turing machine, right? So we want to kind of look at, all right, if I make a more abstract language that's easier to read than this and maybe more compact, how can I know that that language captures everything that Turing machines can capture, right? Fair question? Okay, so then once I have a language, and let's say that we've argued that that language is Turing complete, meaning we know that anything you can do in this language can be implemented by some really, really nasty looking Turing machine. Are there things that can't be implemented with a Turing machine? So if I say Turing complete, right? This begs the question, or even computable. Let's just use that word. Are there things that aren't computable? Right? The very fact that we have the word computable sort of means, well, why would we even talk about computable if everything were computable, right? So it sort of begs the question, well, are there things that are non-computable? Okay, what would that look like? What would that mean? Okay, so we'll get to that towards the end of today to sort of pose the question in a more technical sense. But I mean, you guys can guess the answer. If we're asking the question, what should the answer be? Is everything computable? No, because otherwise we wouldn't be asking the question, right? This would be sort of a done deal. Um, yeah, so it turns out that not everything is computable, meaning that there are things out there that cannot be done by a Turing machine. Getting a sense for what that looks like or what that means is a little tricky. And like I said, we'll sort of pose the question in a more precise way, and a way that we can maybe get our hands on a little bit better towards the end of the day. Okay, good. All right, now let's talk about another way to write, Turing machines, if you will. Okay, and this is using a language, okay, called BareBones. All right, so let me, oops. Okay, so BareBones is a language that's described in our book, okay, and the person who wrote this is, this was what, 15 years ago. Um, the bare bones language is exactly that. It's very bare bones. Okay. These are the only commands that exist in the language, and some of these go together. So, clear, basically, that sets a variable to be 0. Copy, you copy something to something, so that gets us copy and 2. Decker, what do you think that stands for? Or inker, yes. Yeah, decrease and increase, or it's actually decrement and increment, meaning add one or subtract one, right? So to decrement, you take one away from a thing. To increment, you add one to a thing. Do we have Turing machines that can do those? Yes, right? We've got an incrementer and a decrementer. We built both of them, okay? Um, and then there's this while thing. The not we'll talk about. How would we build a Turing machine that can look at a given number and decide if it's equal to 0 or not? Well, what do you think? Yeah, if you scan through the squares and you hit something that's not an X or a 0, namely you hit a 1, say if we do it in binary, then it's not equal to 0, right? Whereas, how do you know if it is equal to 0? No ones. All you hit are zeros, and then in our case, if we put an X at either end to sort of delimit the number, um, then that's that. Yes? Okay. So can we tell whether or not numbers are equal to 0? Yes. Can we increment and decrement? Yes. Can we copy a number from one place to another? Well, we could build a Turing machine to do that. That's not rocket science. Clear, which would be setting something equal to 0. Um, yeah, we can do that. Um, and that's basically it. Okay. So looking at this list, basically everything you can do in this language called bare bones is right here. And I claim that even the clear is not even truly necessary. Um, so does it seem pretty bare bonesy? Okay. What seems like it's missing? Okay, there could be a lot of answers to this question, right? What seems like it's missing out of this is everything you can do in the language is that. Okay, so all the arithmetic expressions, right? Can I do addition? Is there a plus symbol anywhere here? Except for adding 1. okay? And so what I claim is that we can still do addition by building it out of these primitive pieces, similar for multiplication or subtraction or division or whatever, right? Okay, so even though the arithmetic instructions are not obviously present here, we can still get them, okay? Anything else that seems missing? Okay, fair, recursion, and that's a big one, right? Because recursion's kind of a pain in the butt. Um, let's just leave that one on the table for now. Okay, fair point though, right? What else might seem missing? Okay, fair. Um, so we'll take this start to mean, okay, because we had a start state in our Turing machines, right? Um, in most programming languages, you just read them starting with the top instruction, and then you move to the next one, and then you move to the next one, and so on. Okay, so starting will just be, well, you just started. Okay, I know that's kind of stupid when I say it that way, but yeah. Okay, what else seems missing? Huh? So borrowing. When did we need the state borrow? When we were doing the subtract one thing. Okay. So, yeah, maybe it's not explicitly written, but in some sense, it's kind of buried in this decrement thing, right? Because when you decrement, you may have to borrow if you're writing it in binary or whatever. Okay. Um, but could we also imagine, though, that there are plenty of programs for which borrow means nothing, right? When do you need to borrow? Only when you're doing subtraction. Okay. If we're not doing subtraction, then there's no need to even mention borrowing. Okay. Whereas, like, say, for the addition, we might have to carry instead of borrow, right? That was sort of the analog. Okay. What else that seems missing? What about if then else, right? Conditionals. Loops are kind of there, right? Because we have a while loop. And I'll show you how the while loop works in a moment. Okay. Um, so, but like, is a for loop there? No. Are conditionals there? No. So somehow we have to build them out of the primitive pieces. Okay, so let's start with just a real simple example. Um, and um, let's do, let's see what we call this. All right, I'll do countdown and I'll say this. While in not zero do, and then it gets an end at the end. Okay, what am I going to do if n is not equal to 0? I'll decrement it. Okay, so in this program, have I specified the value of n? No. But if I have a value of n, what's going to happen to it? I'm going to take one away continually until it hits 0. Okay, so all of the while loops in this language are set up like this. While something is not 0, do something. Okay, what would happen if I did not decrement n? What would happen to the loop if I never took one away from it? It would just keep going. I'd be in an endless loop. Okay, so I could very well end up setting up an endless loop if I'm not careful. Yeah, could we imagine a Turing machine that goes into an infinite loop? Yeah. Okay, we can write one in a second, but let's concentrate on this first. Okay, so I'm going to write this, and the way I can run it, BareBones n equals, let's just say 10, and then what was the name of the program I called it? Countdown.bb. Okay, so what this will show me is what did I start with as the value of my variable n? 10, and I just picked something, right? It didn't really matter. And what's the final value of my variable? 0. Okay, now that makes sense because what was the code here? So n started at 10, Is 10 0? No, so I'm going to decrement it. Now what's in? Is 10 or is 9 0? No, so now what's in? 8, 7, 6, and so it counts down until it hits 0. And in this case, after this loop finishes, what's the rest of the code? Well, there is none, so the program terminates, right? So we're done. Okay, now that's not the most exciting program on the planet, okay? But let's spice this up a little bit, okay? Let's say I specify two numbers, okay? And so what I want to do is I want to be able to run the following. Let's say x equals 5, y equals 3, and I'm going to call my program adder.bb. Oops, that's not what I meant to type. I meant to do. Okay, now it's going to lodge a complaint because there is no adder.bb program yet because I haven't written it. Okay, so what do you think I want this program to do? I'm going to give it two numbers, x and y, and I would like it to add the two together. Seem like a reasonable thing to do? And what, pray tell, would we hope our answer is? I would really hope that it's 8. Okay, so let's come in here. Now, we already discussed, do we have the ability to just add two numbers? Is that part of our language? No, it's not. But that's somehow what we want, okay? So how could I do that? Well, let's maybe think back to, and you guys may not remember this, or how many of you have like a younger brother or sister that's like 4 or 5 years old, roughly? Yeah. Or they were 4 or 5 years old at some point in the recent past. Yeah.
Recent past.
Like a few years. No? Okay. Yes, you do? All right. Did you ever help them with their math homework? Do they even have math homework? Okay. So, what about you? Did you ever help them with math homework? Okay. So, how would you explain 5 plus 3 to somebody that's in kindergarten? Okay. So, how would you explain that if you were using their fingers? You got 5 fingers, and then add 3 more fingers, and how many fingers do you have? 8. Okay. Let me rephrase it another way using our candy. Let's say you have 5 pieces of candy and 3 other pieces of candy. And I want to know how much candy is here. Well, what could you do? You could say, all right, how many is in this pile? 5. In the other pile? Okay, so I'm going to take 1 from this pile and put it in that pile. How many are in this pile? How many are in that pile? 7 and 1. Okay, so what have I done? I've incremented one pile and decremented the other pile until the other pile has nothing in it. That sounds familiar. How might we translate this into this bare bones language? What do we want to call my second pile? Y? Right? So I'm going to think of two numbers here, X and Y. So let's think of X as being the pile that had 5 in it, and Y as being the pile that had 0 in it. So I want to do something. Okay. What did I do to X? I incremented it. And what did I do to Y? I decremented it. There's our addition program. Right? And this is working exactly the same way as I did with the pile of candy or the fingers for children. Okay? Does that make sense? Yeah? All right, let's make sure it works. And look, what's X? 8, which last time I checked is 5 plus 3. Okay? So it works. Right? Now, how many of you guys think I'm insane for thinking about addition that way? You think I'm insane? Okay. Well, okay. let's be fair. Did you think I was insane before I showed you this method of doing addition? Yeah, okay. So you already thought I was insane. I've just confirmed that I am in fact still insane, right? Okay, so why do you find that to be kind of insane? Okay, very good point. Okay, which is another way of saying the same thing, right? That if the numbers were really big, particularly if the second number is really big, this is a ludicrous way to do it. Okay, it's ludicrous from an efficiency standpoint. Is it ludicrous from a conceptual standpoint? Well, I mean, we could argue about that, right? I mean, I'd say it's not crazy from a conceptual standpoint, right? Um, you might look at this and, if there's any one thing I've learned over my years of teaching is don't poo-poo things that seem too easy. Um, so, for example, you could look at this and say, Dr. McKinney, we are not kindergartners. You should not be teaching us to add as if we're kindergartners. We're 18 to 22-year-old young men. We are perfectly capable of doing real arithmetic, right? Are you though? Touche, right? Well, as we found out, some of you are incapable of logarithms, right? I mean, how many of you were learning logarithms in elementary school, though? No. When did you first run into logarithms? Okay, which year? Which grade? Eighth grade? You hit logarithms? Oh, okay. I didn't see him until ninth grade, but whatever. Future math professor back there. No, okay. Um, yeah, actually, I, my high school. How many of y'all's high schools worked like this? So, in any given semester, I only had four classes, but they met for an hour and a half a day. So it was kind of like a college schedule. Did anybody have a system that worked that way? And then you flip for the other ones. Okay, so it'd be like that, but you do all of the first four in the first semester and all of the second four in the second semester. That's how my high school was set up. And I loved it. Do you know why I loved it? Because I could take math at twice the rate that I would have been otherwise able to otherwise. So first semester freshman year, what did I do? Algebra 2. Second semester, trig and pre-calc. Third semester, calc AB. Fourth semester, calc BC. And then I said, screw you guys, I'm going to college. Um, so yeah, that's a long story. But point being, right, you ran into logarithms at some point in high school, right? Not middle school or elementary school. So this view of addition might seem really, how to put this, like overly basic, right? But what's the advantage of thinking of addition this way? Incrementing and decrementing, can we do those two things with a Turing machine? Can we tell whether or not something is equal to zero with the Turing machine? Yeah. So it's perhaps, well, obvious is too strong of a word here, but it's probably clear that if we sat down and really got our hands dirty with the Turing machine, we could build a Turing machine to do exactly this. Okay? Yes? Or we wouldn't have to because that was actually the example I showed you was essentially this. Okay? So what this means is that if we can do these things with the Turing machine, the increment, the decrement, and the this sort of loop construction, then anything we can build with these is to already Turing complete, right? So, and of course, this language is called BareBones for a reason, okay? Because like we don't have a whole lot to work with. Um, that said, something funny that's been circulating on Facebook and seems apropos given that it's Halloween uh, is a picture of like somebody who went to like a Walmart or a party store or something, and they've got the various Halloween decorations that you could put out, and you would expect to find some skeletons and bones and other parts, right? It was a spider skeleton. Now, why is that hilarious? Because spiders don't have skeletons; they have an exoskeleton, and so it's like, wait, what? Anyway, um, okay, so um, let's actually look here. Go back and look at the rest of what's in the language. Okay, so clear. What does clear do? Well, what do you think clearing a variable does? Just sets it equal to 0. Okay. Do I need to actually have clear as a part of my variable or a part of my language? Okay. So I claim that we don't, strictly speaking, clear is not necessary. It's convenient, but it's not necessary. Okay. So let's suppose that I have a variable. In fact, let me call this um, so let's suppose that I'm going to pass this function a number n. Okay. How can I make sure that n gets to be 0? I could do this. Okay. But I claim I don't have to. What else could I do? While n not 0 do decrement n end. Okay. Which, we've actually already seen that program, right? I just called it, what did I call it at the beginning? Countdown. Okay, so if I ran this with, let's say, n equals 50, then what does n end up as? 0. Okay. Now, here's an interesting question. What happens if I set n equal to 0 to start with? Does the loop actually do anything? No, because it was already 0. Okay. So what does this show? Do I need the clear statement? No, because I could build it out of the while and decrement. Okay. And so we could even imagine taking this clear one and getting rid of it. Okay. Similarly for copy, how could I copy one number to another? Decrement one and increment the other until the first one is 0, right? Okay, so I could get rid of that one too and simplify this and maybe have bare bone instead of bare bones, right? Just here's the femur, right, on the table. Or maybe do like Hamlet and have a skull in your hand, right? Because no good speech is done without while holding a skull. You guys know Hamlet, right? Yes. To be or not to be. Okay. Just making sure. It's better in the original Klingon, by the way, but yeah. Okay. Init, that just allows you to set the value of a variable at the start of a program. And we basically talked about all of these, right? So this language, would you guys agree, is more convenient than bare Turing machines? Okay. Is it less convenient than Python? Right? Because as we've seen, there's some stuff that appears missing, right? But this is simple enough that we can see that each of the individual pieces can be implemented with the Turing machine. And as such, every combination of those things can also be implemented with the Turing machine. And so this language is, as simple as it is, Turing complete. Okay, so it kind of makes sense? Okay, so what other things could we write in this language? Well, let me just show you some examples. Okay, what's the factorial? Right, what's 5 factorial? 5 times 4 factorial, or 5 times 4 times 3 times 2 times 1, down to 0. Okay, so let's kind of look at this code and think about just briefly what it's doing. So first off, did I ever say that you couldn't nest things inside each other? Of course not. That's the whole fun, right? So what's true about these while loops? They're nested. Okay. So if we think, like, what's really the hard part about doing the factorial? What do we have to do with the factorial? We have to do multiplication, right? Okay, now in the factorial case, it's a very specific kind of multiplication, right? Because what are we doing? 5 times 4 times 3 times 2. Well, there's nothing to do with times 1, but yes, okay. So let's maybe change the question and say, all right, forget worrying about a factorial. Let's just think about how we might do multiplication. Okay, seemed like a reasonable question. All right, so let's think about it. Let's say I wanted to do 5 times 3. We've already figured out how to do 5 plus 3. How might I think about explaining 5 times 3 to a child? 5 plus 5 plus 5. Okay, does that make sense? Yeah. Now, this only works, by the way, for integer multiplication, but we'll restrict ourselves to that, right? It doesn't make any sense if you want to multiply by 3/4 or something, right? Because then you have to think a little harder. Okay, so let's say I want to do 5 times 3, right? How am I going to conceive of this? 5 plus 5 plus 5. Okay. Well, how do I do 5 plus 5? Right. I do the increment decrement trick, right? The old Texas two-step. Okay. So how do I think of 5 plus 5? I think of incrementing 5, decrementing the other 5. So 5 plus 5 becomes 6 plus 4, 7 plus 3, 8 plus 2, 9 plus 1, 10 plus 0. Right? Does that make sense? Okay. All right. So let's see if we can figure it out. Okay. So anything in this language, by the way, that's on a line that has a hash mark, the hash mark denotes a comment, and that just means it's ignored by the BareBones program. And so anything I type there is just a comment. It's ignored, right? It's like scratch paper or something. Okay. So if I have two numbers, X and Y, let me do this. Okay, so what does that do? And again, let's sort of pretend that X is 5 and Y is 3, just for sake of keeping track of the things in our head. What is copying X to some other variable? I called it XX, who cares? Right, what is that doing? So let's say that X is 5. What's the value of X? What's the value of XX? Now also 5. So I have two copies of the same number, right? Maybe that'll be useful. We'll find out, okay? So what do I want to do? I want to add X to itself Y times, okay? So I'd want my program to look something like this. While Y not 0 do, and I'm going to put a comment here, add X to itself, okay? What else do I need to do? I need to decrement Y, okay? So that blue part where it says add X to itself, well, how do I add X to itself? Yeah, copy it and increment, okay? So I do something like, well, let me do this. Let me copy it to N, and then I'm going to do while N not 0 do. Okay, what should I do here to x? Increment it. Okay, so let's think about this. I made a copy of the number xx. Yes. Should I decrease in? Yes, good call. Thank you. Because otherwise I'll be in an endless loop. Okay. Okay, so let's think about what we're doing here. So why did I copy x to xx? Well, I'm going to use x as my running total. Xx is just going to be what the initial value of x was, okay? And then n I'm using here as a counter. But every time, how many times do I need to add x to itself? 5 times, right? But this number n changes, and so I'm going to reset n basically each time I go through the outer loop, okay? Let's run this and see if it works. Yes? No? All right. All right, so what did I call this? Mult bare bones, x equals 5, y equals 3, mult.bb. All right, I have definitely screwed something up.
You said you were multiplying x n times and you said n was 5.
Almost. Huh? It multiplied by 4, not by 3. Why? Okay. So you guys, what did we get as our answer? 20. Okay. Would you guys agree that's incorrect? Okay. But what is 20 in terms of 5? 5 times 4. Okay. So maybe I've actually overdone it somehow. So let's go back to the code and see if we can fix it. Okay. Actually, why don't we try this? Well, that's definitely not right. All right, let's see if we can find our problem. Interesting. Oh no, I see what I did. I need to do, no, because what I'm doing, right, is x plus itself here, right? So x should be involved and x should be involved. Okay, so I copy xx to n. So what was xx? It'd be 5. I make that n. So while 5 is not 0, do, yeah, I think, okay, actually, let me try this. There we go. Okay, I just took 1 away from y at the beginning. And
You're adding that 5 to itself 2 more times.
2 more times, exactly. I already have a 5, right? Okay, so yeah, that's the mistake, right? Now, let's say I could actually undo that if I did the following. Um, I could do clear x. No. Um, that's what I need to get rid of. Yes. Okay. So I could also do this, right? Okay. So yeah, good call. Here, I started with x as being, I was sort of using it in two ways. I was using it as a running total, but there was already a 5 there. So how many more times do I have to add 5? Not 3, but just 2. Okay, so I have two options for the fix. One is to just take 1 away from y, right? Or wait a minute. Did, did I actually need this line? I never used YY, did I? No? Okay, so I can get rid of that. Okay, so I could either take 1 away from y. Oh, wait a minute. What did I just do? Did I not delete this? Oh, that's weird. Okay, I could either take 1 away from y from the get-go, or I could just reset x to be 0, because of course I've made a temporary copy of it over here as xx. Which way makes more sense to y'all? I mean, they're both equivalent, obviously. Clearing x? Okay, fine. So we'll just do it this way. All right, and let's make sure, oops, that it still works. Okay, give me some other numbers. Okay, 9 and 7. 63 looks good, right? That certainly matches the finger trick slash, you guys memorized your multiplication tables back in school, right? You all know the finger trick, right? Right? You don't know the finger trick? Oh, this is so awesome. This only works for multiplication by 9. But here I'm doing 6 times 3, right? So hide your seventh or your sixth finger. So I've got 6 times 3, right? Um, Wait a minute. Did I do that right? That's right. So I've got 6 fingers, right? These 5 plus this one. So I'll hide my 7th finger, right? So what's the answer? 60. Sorry. What were we doing? We were doing 9 times 7. Okay, I'm sorry. I've got myself confused here. So 9 times 7, hide your 7th finger. And what's left? 6 fingers and 3 fingers. 63. Okay. Let's do 9 times 4. So I'll hide my 4th finger. 36. Yeah? Isn't that kind of cool? Did you guys not learn that in school? Really? Wow. You memorized a damn table?
You memorize up to 5, and then it should, or up to 4, and then it should split.
Okay, that works too, right? Yeah, you guys never learned that. It's remarkable to me because that's like so easy. Um, it's so easy a caveman could do it, right? And Geico could save you 15% or more on car insurance. No? Okay. All right, so let's just sort of tie off here. Let me leave y'all with a question to ponder for next time, okay? We've written some programs in this language. We've also built some Turing machines. If I gave you a specific Turing machine or a specific program, could you look at it for a few minutes and figure out, yep, this program is going to terminate? Or, nope, I think this program is going to run in an endless loop forever. You think you could handle that if I gave you just one program? Probably, right? If it were thousands of lines long, maybe not, but if it were only like 5 or 10, you could probably figure it out, okay? Okay, here's the bigger question. If you could do it for a specific program, do you think you could make a program that could do it for a specific program? Yeah, you guys are programs in some sense, right? Bigger question. Could I come up with a program that could read any program and determine whether or not that program halts or not? Okay. The answer is no. But I want you to ponder about why that might be the case. Okay. This question is called the halting problem, and it's not possible. And we'll talk about kind of the details of it on Wednesday. But I just want to leave you with that to sort of ponder the question. Okay. All right. Have a good rest of your day.